My talk is about FlowTags, which is an extension to software-defined networking to enable network-wide policy enforcement in the presence of Middleboxes. So we just had an excellent talk on SDN. Essentially, a key advantage of SDN is the ability to provide a set of high-level specifications for the logic that we would like to implement in the network, and then being able to translate them into data plane configurations. And in fact, we've seen a lot of progress in this space over the past few years. But certain network management tasks, such as service chaining and access control, are difficult in the presence of Middleboxes. And this happens to be a fundamental issue because Middleboxes are a key part of today's real-world data planes, either in form of physical appliances or virtual appliances. The key problem here is that Middleboxes such as NATs, load balancers, and proxies modify packets in a traffic-dependent and dynamic manner. So to gain some insight into what kind of problems I'm talking about, let's look at a couple of simple examples. So here in the first example, we would like to block host H2's access to certain websites, which is a very simple policy with regard to security of the network. But the problem here is that by the time the traffic from our host gets to the firewall, it has been already modified by the NAT. So essentially, the firewall is not able to attribute the observed traffic to its true source. Essentially, the firewall cannot distinguish between different hosts. Therefore, our policy cannot be enforced. Here in the second example, we are using a web ACL device to enforce a very simple policy, which is essentially blocking host H2's access to some website XYZ. But things can go wrong if the proxy provides a cached response to host H2. Essentially, what we see in this case is that the dynamic behavior of the proxy is violating our intended policy. And there are many other examples of this kind. So having seen such examples, we might think of some candidate solutions, such as trying to place Middleboxes in a certain correct physical order, hoping for the right thing to happen, or try to tunnel the traffic through the sequence of intended boxes in the network, or even try to use consolidated virtualized platforms, or even try to correlate input and output traffic of each given Middlebox from an external point of view without actually going through the logic of the Middlebox. But it turns out these candidate solutions are only partially successful because what they do, they're addressing the symptoms of a more fundamental problem. Now, what is that root cause? So to see what the root cause is, it is useful to go back to the original work in the SDN space. So if we go back to the original work on SDN, papers like Ethane, so there are certain SDN tenets that were envisioned by this early work. One of them is origin binding, which essentially says there has to be a strong binding between a packet and its origin at all times and all locations in the network. There is another tenet, path follow policy, which says the path that the packet takes in the network has to be determined and mandated by explicit policies that we have defined prior to network operation. Now, what happens with Middleboxes is that Middleboxes violate both of these SDN tenets, and that is the real root cause of the problem. So what we do in FlowTags, we provide an architectural solution to restore these tenets and enable network management tasks such as policy enforcement and diagnosis despite Middlebox actions. Let me give you the high-level idea of FlowTags. Essentially, in FlowTags, we believe because Middleboxes are the root cause of the problem by violating these SDN tenets, they are in the best or sometimes in the only position to help us restore these SDN tenets. And this requires minimal changes to Middleboxes, as we will see in the following slides. And the key idea in FlowTags is to add and use missing contextual information inside packets. For example, a NAT, among other things, modifies packet headers, and this is missing pieces of information that are going to be material in policy enforcement. So this is something that we would like to encode as tags. Or in the case of a proxy, it's even worse because not only the header is modified, also there are dynamic actions involved such as cache hit or cache miss that can make things go wrong. Essentially, we would like to capture these pieces of information also as tags. And what we are doing is in the context of SDN, so essentially FlowTags controller is in charge of configuring and controlling network-wide tagging operations. So let's look at the FlowTags architecture. This is today's SDN architecture, where SDN switches are interfaced with the controller using existing APIs such as OpenFlow. The problem with respect to architecture of today's SDN is that Middleboxes in this environment are treated in an isolated way as separate devices. And this is really an issue. So what we really want to do is integrate Middleboxes as a natural part of this ecosystem. So we envision 4 changes to today's SDN architecture. Essentially, we extend that on 4 fronts. One of them is enhanced Middleboxes that are capable of capturing tagging operations across the network. We need new FlowTags APIs between these enhanced Middleboxes and the controller. On top, we need new control applications for tasks such as policy enforcement, verification, and test. And finally, we need to provide the operator with explicit APIs in order to specify intended policies that we would like to enforce in the network. So in particular, we are not changing existing APIs between the controller and SDN switches, so we can keep using, for example, OpenFlow. Also, we don't change anything about SDN switches, and this is a deliberate design choice to enable switch and Middlebox vendors to innovate independently. Okay, so now let's see why this tagging idea could be helpful to enforce policies. Let's look at an example, the same example of the proxy and the ACL. Now this time using FlowTags. So if we have this tagging mechanism in place, let's look at traffic coming from host H2 requesting website XYZ. And remember that our intended policy was to block such access. Now, using FlowTags, what happens is the proxy is a tag generator, which means it is going to be encoding critical information as tag values. In this case, what we really want to encode is the source IP information of host H2, and also the fact that this is a cached response at the proxy. So suppose tag value 2 is capturing this semantic. So this tag value 2 is going to be embedded in the packet. Now, why this is useful? Well, going forward now at switch S1, the switch is going to be consuming this tag value, which means it's going to look up the tag value and decide what the correct next hop is. In this case, it simply says, OK, next hop is switch S2. Similarly, switch S2 is going to be consuming this tag value to find the correct next hop as per our policy. In this case, it's going to send it to the ACL device. And finally, the ACL device is a Middlebox that is a tag consumer, which means it's going to decode this tag value and map it back to whatever it cares about. In this case, what a web ACL really cares about is the origin source IP, because our policy is based on different hosts. Now things are very easy because we have access to the source IP information, and the ACL drops a packet as we intend. So this example shows that how an orchestrated use of tag generation and consumption operations across the network enables us to enforce our policies as we intend. But how do we do this? There are certain design questions before we can realize this tagging vision, FlowTags vision. So the first question is, what are the tag semantics that we need to capture? As we saw in the example, the Middleboxes in a FlowTags-enhanced network are going to be adding and decoding tag values. For example, the proxy is going to add tags. The ACL in that example is decoding tags. Also, the switches are going to be using tag values to decide how to forward packets. So essentially, we have these tag-dependent operations. So what semantics should we capture with respect to these tags? The second design question is the role of the controller and new APIs that we need, because as we saw, essentially the Middlebox is going to be consuming and generating tags. So somehow we need to interface them with the controller to enable this tagging logic across the network. And finally, the question is, can we enhance today's Middleboxes to support this FlowTags operations? Because of course, today's Middleboxes don't do such thing as adding and decoding tags. Is it possible? So let's go over these questions one by one. Let's start with the question of tag semantics. So on top here, I'm showing the same example of the proxy and the ACL. So if we are the network operator of this network and we want to enforce the very simple policy of blocking host H2 access to XYZ, The first thing we need is really a way of specifying our intended policy in an unambiguous and clear way, which is missing today. Because related work today talks about policy chains, and a policy chain is essentially a sequence of Middleboxes for different classes of traffic. We can think of classes of traffic as different departments in our company or on our campus. But that is not able to capture Middlebox semantics. So what we propose and use instead is the notion of a dynamic policy graph, or a DPG. Now, what is a DPG? So the first thing we need to model to specify our intended policy are the end hosts or endpoints of the traffic. So in this example, we have two hosts, so correspondingly we have two nodes in the DPG on the left, H1 and H2. Also, the internet and the drop are being modeled as endpoints because some packets are going to be dropped according to our policy. Also, we have two Middlebox functionalities here, a proxy and a web ACL. So essentially, we have two nodes to model these Middlebox functions. And of course, we have the interconnection of these nodes. Now, as you can see, each edge is annotated with the corresponding transition condition. So let's focus on the case of traffic going from the proxy to the ACL. So as you remember from the example, the tricky case was when H2 is requesting xyz.com and it is cached at the proxy. So using this notion of DPG, we are able to say that in the case that the traffic coming from host H2 and it is a cache hit, still we want to send it to the ACL and to be able to enforce our policy. So essentially, a DPG is a way of stating our policy that we would like to enforce in the data plane while taking into account Middlebox actions that could be dynamic and traffic dependent. So now why do we need tags? Well, if we want to implement this graph in our data plane, we should be able to essentially determine the next hop at each node of this graph, which means we need to have enough information to determine what transition is going to be triggered. In this case, but the proxy is hiding both pieces of information, namely the origin and the hit miss information. So the role of tags in this case is to provide us with this information which would be otherwise missing. Therefore, intuitively, we need a distinct tag value per flow, per edge of DPG to be able to enforce our policies correctly. Okay, so the second design question is the role of the controller and new APIs. So what APIs do we need? Going back to the example, the proxy was generating tags. So somehow it needs to figure out what tag values to use for a given source IP and cache hit, which is its context. So for this, we have designed and implemented generate APIs between Middleboxes and the controller. On the other hand, the ACL is a tag consumer, which is going to be decoding tags. For that, also, we need to have APIs between Middleboxes and the controller. These are new APIs. And we saw that switches are going to be consuming tags, essentially deciding how to forward packets based on tag values. But for this, we don't need anything new. Essentially, we can use, for example, OpenFlow because it is already providing whatever we need. And also, SDN switches are supporting these operations. They can match against different header values. So now what is the role of the controller in FlowTags? The SDN controller has three main modules. The first thing we do before we run the network is that we specify our intended policies using the notion of DPG, a dynamic policy graph that we saw in a couple of slides back. And the first component is in charge of translating this DPG into a data plane configuration. Now, after this, we have the network up and running based on our intended policy. After this point, the controller is a reactive controller, which means it's going to react to new flows coming into the network. There are two types of event handlers corresponding to Middleboxes and switch events. For Middleboxes, we have Middlebox event handlers that process tag generation and tag consumption queries coming from Middleboxes. These are new event handlers. Also, we have switch event handlers that react to events such as flow expiry, or they take care of essentially installing new forwarding rules. And this is similar to today's SDN. So these are the three main components of the controller. And finally, the question is, can we enhance today's Middleboxes to be able to support FlowTags? To answer this question, let's look at a typical Middlebox, irrespective of its particular functionality. So essentially, a Middlebox is a bunch of modules, packet processing modules, that translates the input traffic to output traffic. At a very high level, this is a given picture of a Middlebox. Now, the first strategy to add support for flow tags for tag generation and consumption is to essentially don't change anything about internal modules of the Middlebox and only add the tag generation and consumption logic at the input and output choke points of the Middlebox implementation. This is shown in yellow in this case. So these are essentially lightweight packet rewriting shims. And this takes very minimal modifications, but on the other hand, it might be hard to get internal context of the Middleboxes. For example, if you are thinking of a proxy, using this strategy probably is unlikely to get cache hit or misinformation. Therefore, we have a second strategy, which is module modification. And in this case, we really go ahead and modify individual internal modules of the Middlebox to add support for tag generation and consumption. In this case, we need to do a little bit of more work, but then we have better access to internal otherwise hidden information. So what we do in FlowTags is essentially a hybrid. We take a hybrid strategy. For tag consumption, we take the first strategy, packet rewriting, and the reason for that is once we look at the input packet and we decode it once, then we can send this decoded packet to different modules of the internal modules of the Middlebox. But on the output side, that we want to do tag generation, we really need to have access to internal information of the Middlebox. Therefore, for tag generation, we take the second strategy, which is module modification. So to see the visibility of FlowTags vision, let's look at some of the evaluation results. There are a few evaluation questions, but I'm going to be focusing mainly on two questions. One is feasibility of Middlebox modifications. The other is FlowTags overhead. And also I have a summary of other results. So here in this table, I'm showing 5 existing open source Middleboxes that we have modified to add FlowTag support. In the second column, we see the total number of lines of code of the existing implementation of the corresponding Middlebox. And in the third column, I'm showing the number of lines of code that we require to modify in the Middlebox to add FlowTag support. So as we can see here, we really need minimal modifications to add FlowTag support for Middleboxes, existing Middleboxes, and this makes it practical, really. So let's look at the overhead of FlowTags. So here in this plot, the x-axis is showing different topologies, different network topologies, and different number of nodes in the network. And the y-axis is showing new flow setup time. So in each case, the green stack is switch setup time. That is something that happens in today's SDN using OpenFlow, for example. So what we add as the overhead of FlowTags is shown on top 2 stacks, one of them in orange, the other in black. And essentially what we can see is, here is that the fact that the overhead of FlowTags is minimal with respect to what is already happening in SDN. And also, let's look at some summary of other results. So we have measured the overhead of adding FlowTag support to different Middleboxes, individual Middleboxes with respect to processing time and memory. In each case, it has been consistently less than 1% because they are very low complexity operations, algorithmic-wise. The second thing to mention here is that the number of bits that we need to encode these tags in packets, in the worst case, was fewer than 15 bits, and there are a number of ways to accommodate this number of bits depending on the particular network. And finally, because essentially FlowTags provides otherwise hidden information of the internals of Middleboxes, it enables building new tools for example, network verification based on extensions of header space analysis. It also enables new diagnosis tools to find bottleneck elements of the network. So to summarize, Middleboxes complicate policy enforcement because of packet modifications and their dynamic and hidden actions. And the root cause of this problem is that they violate SDN tenets. So FlowTags extends today's SDN architecture with new Middlebox APIs to restore these SDN tenets. It doesn't require any changes to existing SDN switches and existing switch APIs such as OpenFlow. And FlowTags is practical in that it requires only minimal changes to existing Middleboxes and poses low overhead. And finally, it is an enabler for new verification, testing, and diagnosis tools. Thank you.
Is it possible, again, I'm wondering, is it possible to implement these DPGs entirely within the data plane without sending any packets up to the controller? You mentioned that your controller is reactive.
Right. So the very first step is that we are given a DPG. So we specify as network operators a DPG, and then we can automatically embed it in a network, implement it in a network. And beyond that, per new flow, we are reactive. And the reason for that is because we don't know what flows we are going to see unless we assume something. Therefore, and this is a typical approach in today's open flow. You have basically this round trip between the controller and SDN switches per new flow. But for the following packets of the same flow, you are caching these tag forwarding rules inside network elements, and you don't need to query the controller. This is exactly identical to today's open flow logic.
Sorry, open flow. My understanding is that, like, for example, this VMware talk we heard yesterday, they do everything entirely proactively. I guess because, like you said, I guess because they can assume something, they enumerate the entire
Exactly. So it depends really on the granularity of policies. For example, if you have 10 departments and your granularity of policies is department-wise, you can go ahead and proactively install rules. But in the worst case, there are huge number of possible flows, so you cannot be reactive in that case. So it really depends on what network you are considering.
Okay, great, thanks.
Yep.
Hi, cool work. 2 questions. One is, how granular are these flow tags? Your examples give the impression that this is some Cartesian product of host and some attribute of the policy or some combination of attributes of the policies. And then yet you claim you essentially could fit it in 15 bits. So that's one. And then secondly is, whenever a policy changes, right? Earlier, when an admin used to go and change a Middlebox policy, it was a local operation. Now, essentially, this is cascading potentially because you would now have to adjust the flow tags across the entire end-to-end path. So does it introduce some consistency when you essentially even have multiple policies being changed? Right. So could you comment? So
the first question with respect to the number of tags you need. So the number I showed you here is in the worst case that you have a very huge trace, like 70, 80,000 new flows per second, and you have different policies per flow, and which is a very unlikely case, and in that case it's like 14. But it really depends what granularity of policies you're considering into your network. So if it is per flow, then yes, per flow you need to be able to distinguish, because by definition you want to do different things for different flows. So can you remind me of your second question?
Yes, essentially, is a potentially cascading effect of whenever a policy changes a problem in your system? So if policy like DPG, the dynamic policy graph, is that what you mean? No, by policy as in Middlebox policy, essentially, for example, changing allow deny rules. Well, that's right. So you need to essentially be able to translate your new configuration and initialize your network. So this is something that typical of today's networks too. So this is not something that we mandate. No, so I guess my question was, a single policy change to a Middlebox, can it cascade? Because now you have to adjust the flow tags across the entire end-to-end path. So if you think of the graph, if the path is independent, then you don't need to change other paths of the graph. You only need to change the affected parts of your policies, which is necessary for the correctness of your policies to ensure that everything goes fine. Thank you.
Quick question. I was wondering, like, have you considered Middleboxes where the input traffic is not equal to output traffic, like, for example, WAN optimizers? How will you going to tag the traffic? By equal? Like, it can merge different flows together, right, to compress traffic, or on the other side, it can decompress. That's right. So in FlowTags, we support that. Essentially, you have a multi sort of input packets to one packet output. So we can capture on the output packet, our tag value says which input packets this is equivalent to. But the problem in this case is more of a logical problem, which means what kind of policy would you like to enforce? Because your input packets could be coming from different departments that you would like to enforce different policies to. But in this case, you have only one output packet. So it's more of a question of the correctness that you would like to consider. But as FlowTags, yes, we capture that. Thank you.
Hey there, nice talk.
Thank you.
Josh Reich. Could you just go back one slide? I think it's one slide. Yeah, so in terms of the various ways that spaces where you're thinking of putting these tags in, are these mechanisms standard to OpenFlow currently?
In this space for storing tags?
Yeah.
No, in OpenFlow you don't have the notion of tagging necessarily. In OpenFlow you have other possibilities for like you have a stack mechanism of pushing tags. You can do that here. The reason we consider these essentially headers is that they are sort of universally supported by different Middleboxes. Essentially you could do any header, but these seem to be headers that different Middleboxes can capture and understand, like IP headers mostly. But you could do anything that you want if your Middleboxes can support that.
But in order not to change the OpenFlow side of things,
right,
you actually need to be able to check these things on the switches as well as in the Middleboxes, right?
This is the main reason that we are using this, because if you consider IP headers, IP header is supported by SDN switches and different Middleboxes, so it seems to be the most natural place. But essentially, any place that is supported by the switches and Middleboxes could be used for tagging operations.
Yeah, so, well, I guess the point
Can you take the rest
yeah.
of the discussion after?
Okay.
Thanks.
Sure.
Okay, let's thank Seyed once again.